Good morning, all of you. So, in the last class, we started our constraint motion. So, in that, we discussed some problems based on the general constraints or the velocity constraints. And so, now let us see some more problems based on the same concept here. So, here, let us write the first problem here. This M1 is a ring which is constrained to move on this vertical smooth rod here. Here, all are smooth only. We need to neglect the friction in any problem here. It's a common. And this is a block M2 is connected here. So, we are releasing the system from here, so that this M1 is moving down. Let us consider M1 is heavier than this of M2, so that this M1 is moving down here. So when it falls through a distance h, we need to find the velocity of this block. So mention that question. In the system shown in figure, a ring of mass M1 is constrained to move on the vertical rod. And in brackets mention M1 is greater than that of M2. Find the ratio of velocities of the blocks. Find the ratio of velocities of the block when a ring descends through a distance h, or when ring falls through a distance h, So simply now this is the given situation. So once if you release this, then it will fall here. So I am taking this situation here when it reaches this position here. So let us see this now. So when it is reaching this position, I am taking this velocity of this block as V1 and velocity of this block as V2 in upward direction. So this M1 is moving down means M2 will move up, right? So then I am taking the velocities like that. And so now let us resolve the velocity components along the length of the string. So we need to resolve the velocities along the length of the string. I am assuming this angle as theta here. So then V1 is actually vertically downwards. So we need to resolve this. So you need to assume always velocities in actual direction of motion. You need to assume here. So actual direction of motion is downward. So that direction we are assuming it as V1. So this is V1 cos theta. You will get that component. And velocity of this block we are assuming it as V2, and that V2 will be in upward direction only. That V2 is along the length of the string only. So according to our velocity concept, velocity along the length of the string must be same here. So then V1 cos theta must be V2, or V1 by V2 is equal to 1 by cos theta or secant theta you will get. And that 1 by cos theta or secant theta you can write by using this triangle, because it is falling through a distance h, and this length is already given L here, and that L will be a constant value, fixed value. So you can write in terms of this L and H, you can define this secant theta or 1 by cos theta value. So this is the ratio of these velocities at that instant here. So that is the problem. Now let us come to this problem here. So then here, note down this problem here. In the system shown in figure, the end A of the string, is pulled horizontally with uniform velocity V0. Then find the velocity of the block B. As a function of time. So that means now here we are assuming like this block is already traveling some distance here. This block is already traveled. In the time t means it travels a distance of V0 into t. Now I am taking that situation here. It is already given that this velocity is V0 along this direction here. So we need to resolve this. So at that instant I am assuming this velocity of this block as Vb in upward direction. And so now I am resolving this into components here. So V0 cos theta you will get along this direction. And so then again our constraint relation must be equal to this V0 cos theta must be equal to Vb. That is our simple constraint relation here. Therefore Vb is equal to V0 cos theta you will get. And that cos theta value you can define by using this triangle. This will be a h value which is a constant here, because it is moving only along horizontal direction, and this value will be V0. So cos theta you can define here. So finally you will get this velocity like this, right? And actually these problems, as we discussed in the previous class, you can also derive by differentiation method here. You can also derive by differentiation, but that method is not required. As you know this velocity constraint, you can solve it easily here. So here also you can use this relation Pythagoras theorem, and here also you can use the Pythagoras theorem here. That means simply if y is the displacement of the block, suppose from here to here this block is displacing by a distance y, then this distance will be h plus y, because initially it is y. So here this block is rising up by a distance y. So here the length of the string will increase by y, because total length of the string is constant. So now you can use this Pythagoras theorem for this triangle and you can differentiate that. You will get the same value there. Now there you need to replace the dy by dt as velocity of this block, you need to replace, right? And then next here this problem here. So just to mention that this ring is constrained to move along this horizontal rod here. So then we need to find velocity of this block when the velocity of the ring is v0. So mention that a small ring is constrained to move along the horizontal rod. A small ring is constrained to move along the horizontal rod as shown in the figure. If velocity of the ring is v0, then find the velocity of the block. So here also you can solve it easily here. Just we am resolving this velocity into components so that you will get v0 cos theta along the length of the string. So that must be equal to the velocity of this block here. So directly I am using that as velocity of block is equal to v0 cos theta. And actually in general in these problems sometimes they will ask like acceleration relations here. Generally in constraint motions, after getting that acceleration relations, we need to differentiate them. We need to differentiate that relations because we know dv by dt is nothing but our acceleration, right? So just by differentiating that relations, velocity relations, you will get the acceleration relations. But here for example, if you are taking for example this problem here, if they will ask like acceleration relation AB is equal to A0 into cos theta. Is this relation is correct or not, they will ask. Is that relation is correct? No, because that means just by differentiating this they are writing this equation here, and there they are treating that theta as constant value, but you can observe that theta is not a constant value. So theta term also you need to integrate, you need to differentiate there. If you want to actually write an acceleration relation for this, then actually you need to write it as dv by dt, and this is equal to dv0 by dt into cos theta plus v0 I am writing directly the differentiation, cos theta differentiation you will get minus sin theta. So minus sin theta into d theta by dt you need to write. So that means that is actually acceleration term there. So this is the acceleration of this block, and this is the acceleration of the ring you will get there, right? So that means just by using this relation, whenever the thetas are included in that constrained velocity relations, you need to observe that if theta is variable, then you will get such a equation. UV formula you need to apply while writing the differentiation. If theta is constant, then you may apply this differentiation directly there. So observe that whenever they are asking such a acceleration relations, then you need to observe this one whether theta is variable or not. And for example, if the system is released from rest, and if they are asking at the instant when the system is released, at t is equal to 0 if they are asking, then at t is equal to 0, that means just the system is released from rest. If you release from rest, automatically this will happen. This block will move down and the ring will move, starts moving along the direction, right? So just after releasing, if they ask in the same question, then this value v0 value will be 0. So that this term will be 0. Then in that case you can write that acceleration of b is equal to acceleration of a0 into cos theta you can write. So this is at t is equal to 0 if you consider here just after releasing. But at any instant of time means you will get such a relation here. So be careful about such acceleration relations there regarding especially for this type of questions there, right? Yeah, next let us see this problem here. Note down this problem. A hinged structure consists of three rhombus with the ratio of sides as 3:2:1, with the ratio of sides as 3:2:1. The end A3 is moving with the velocity v. A3 is moving with the velocity v. Then find the velocities of junctions A1, A2 and B2 when the angle becomes 9 at the instant when the angle becomes 90 degrees. That means this total angle will be 90 degrees. So that is the data what they are giving. That means this is a hinge structure here, so that they are pulling this end with the velocity v. Then we need to find the velocity of this junction and velocity of this junction and velocity of this junction we need to find here, right? So velocities of those junctions we need to find them. Then simply let us see how to solve this. The ratio of the sides of this ratio are in this 3:1:3:2:1, that is already given there. Then the diagonals are in the ratio 3:, the diagonals will also be in the same ratio 3:2:1. Now here I am assuming that this distance at this given instant I am taking it as x, for example here. So then if this distance is x, then according to the given ratio you can take this distance will be 2x and this distance will be 3x you can take here, because the diagonals are also in the same ratio of that sides. And so now I am writing from with reference to this I am writing the distance here. So with reference to this this A0 O will be A1 will be 3x and from here to here will be 3x plus 2x 5x. This one will be 5x A0 A2 and from here to here it will be 6x. And so now the velocities of these points now we can write as the rate of change of distance, because it is a fixed end, the ratio of this velocity, because this velocity now we can write it as 6 into dx by dt you can write, and ratio of this side you can write it as 5 into dx by dt you can write, and velocity of this point you can write it as 3 into dx by dt you can write. Clear? And so that velocity ratio I am directly writing here. The dx by dt will be cancelled when you are writing that velocity. And so then this ratio you will get velocity ratio, you can write this as A1 is to A2 is to A3, velocity ratio will be equal to 3 is to 5 is to 6, the distance of that point from that. And so this VA3 value is already given, velocity of this point is already given, that is moving with the velocity V. Then velocities of A1 and A2 we are writing here. Velocities of A1 and A2 is nothing but velocity of A1 we can write by using simply this ratio I am writing here. If you take the ratio between V1 and VA1 and VA3, you will get 3 by 6. So that ratio I am taking here, 3 by 6 into VA3. VA3 value is already V is given, so that you will get this expression. Then VA2 value is similarly you can take this ratio here 5 is to 6, and I am taking that one, and VA3 value, VA2 value you can write as 5 by 6 into V, right? So now, so that is the velocities of these points here. Velocities of A1, A2 is already completed for us. Our requirement is now to find the velocities of this point B2, right? So A1, A2, our question is A1, A2 and B2. So we already calculated A1 and A2 values here. Now we need to find this velocities of this B2. So for this I am taking this part here. This part of this rhombus I am considering there here. A1, A2 and B2. And then here what I am considering is velocity of this end A2 with respect to A1 I am writing here. So velocity of end A2 with respect to A1 means we can write it as VA2 minus VA1 we can write. And so that's values if we substitute 5 by 6 V minus V by 2. So you will get 5 V by 3 you will get. And so now along the rod the velocities must be same. So this is the velocity now we are considering according to our assumption. This point is at rest, only this point is moving with this velocity V by 3 here. And next what we are doing is we are resolving this velocity into component here. So that the component is nothing but V by 3 cos 45 or A2 A1 cos 45 you will get. That must be equal to the velocity of this B along this direction here, right? Velocity of this B along this direction. And so then and that also this velocity of B along the direction means with respect to this only we are calculating here, because we are assuming this one is fixed here. So then that velocity we can write it as velocity of B2 with respect to A1 we can write it as B2 A1 is equal to this VA2 A1 cos 45 you can write. And A1 VA1 A2 value we already calculated it as V by 3, so you can substitute this value here. So then V by 3 root 2 you will get. Then velocity of this B2 with respect to ground we need to write. So what we calculated is with respect to this A1 here, velocity of B2 with respect to A1 we calculated. Just you can apply our parallelogram law of vector addition here. So then the velocity of B2 we can write it as velocity of B2 with respect to A plus velocity of A1 and plus velocity of A1 we can write. And velocity of this B2 is making an angle of 45 degrees with the horizontal, and velocity of A1 will be along this direction only, and whose value is V by 2. And just you can apply the magnitude. We need to calculate the speed here. So you can apply this parallelogram law formula here, V B2 A1 square plus V A1 square plus 2 V A1 V B2 A1 cos 45, and substitute those values, then you will get the velocities of this end B here. So it is a way of finding this velocities in such a hinge structure there, right? Next, let us see this other type of constraint motion, that is our pulley constraint. So we completed our general constraints or velocity constraints. So now let us see these pulley constraints. And so in pulleys, actually we solved a simple problems like when one pulley is there and two blocks are connected across that, that means a string passing over the pulley, and we derived that simple Atwood mission. And so now there will be more pulleys will be there in that system, and so now let us see sometimes the movable pulleys will be there in that system. And so now let us see how to solve such a problems there. So for example, I am taking an example here. So this is one pulley and this string is passing over this, and here this another pulley is there. So I am taking this another pulley, and this is the one block is there here. So this is another block, and here one more block is there here, right? And so let us name this as M1, M2, and this is M3. I am taking the blocks like this. So now we need to calculate the accelerations of the system and tension in the string here. So for this pulley constraints, there are different methods are there for us. So you can solve it in different ways. So I will explain that the basic method, and I will explain the simple method also, how to solve this pulley constraints here. So let us first discuss about the basic method here. The basic method is nothing but just we consider this, we write the length of the string. So actually if you write this, if you want to write this force equations, and then if you want to solve that, you can't solve that. As I said in the beginning of this constraint motion, you will get less number of equations than the unknowns here. That means more number of unknowns will be there in this problem here. And so then what we will do is we write the constraint relation and then along with that force equation, so that you can solve that equations and you can find accelerations of the blocks as well as tension in the string we can find here. So there are different methods for there. So first I am explaining by the first method here for this pulley constraints. So general procedure for this pulley constraints is we write the length of the string here. So this is the first method we can write here. So the first method for this. So the first method what we can mention here is we can write the length of the string. So length of the string is totally constant because we know we consider the inextensible strings, and so that length of the string is constant here. So while considering this length of the string, so we consider some reference level here. Suppose I am taking this as the reference here, and so then this length I am taking it as x1, this length I am taking as x1, and this distance of this block, this length is a constant value, so you can consider it as a pulley length here. So this length you may consider it as x2. Is it clear why I am not taking this this length? Because this length is already fixed. This always it will be fixed only. So the displacement of this block is nothing but displacement of this pulley only, because pulley and this block are connected here. This pulley is also massless only. All the pulleys are massless, ideal pulleys only. And this length you may consider it as some x3. So if you are all are in same level, you may get the confusion to write that length. So I will change this level here. Suppose I am taking this level as this block is suppose say up to somewhere here, M3 let us take. And so that now this length you can write this as x3 you can write here, right? So this displacement I am taking it as x3. And now let us write the length of the string. So first you need to consider such a variables here. You need to consider such a variables here, x1, x2, x3, x4. And if more number of strings are there, then more constraint relations you will get. So now the constraint relations, you can say that if one string is there, one string means not these small parts here which are fixed. If this length, this total length, one string is there, one constraint relation you will get. If two such a strings are there, then two constraints relations you will get, right? So regarding that Pulley problems here. And so we are taking some reference level. From this reference level, we are taking some variables for this position of the displacements. We are position of the blocks. And in that, the simple method here is to avoid the confusion. If M1 block is there, take that as X1. If M2 block is there, take that as X2. And then similarly, if X3 is there, then take that as M3 block is there, X3. For example, here if you are taking X1 and here if you are taking some X2 and here if you are taking some X3, if you are changing that order, then A1, A2, A3 order also will be different. While substituting in force equation, generally we will do the calculation mistake there, substitution mistake. So to avoid that, so take the same order here, M1, M2, M3, X1, X2, X3, to take it in the same order. Now let us say the length of this string. So length of this total string I am writing here. So that length of that string we can write as length of the string L is equal to. So now length of the string L is equal to, starting from this end here. Suppose this end I am writing here X1, right, plus this length. Next we need to write this length from reference level to this length, that is X2, and again from here to this length, right, that is X3, sorry, X2 only, sorry, this side, this length and this length will be same, X2, and next from here to here, that is X3, right. Now here you may get a doubt like, what about the length of the string over the pulley? So that means here some length will be there here, this length will be there, and similarly some length will be there here, and similarly this some length will be there here. On every pulley some length will be there like that. You can neglect that part because that part will be always constant, or you can take some total that part as some x0 you can consider here. X0 is the length of the part lying, the total length of the part lying on that. In general you neglect that part because that will be a constant. Even this block is displacing by 1 centimeter. If suppose this length is, for example, say 0.5 centimeters length is there, this total length for example over the pulley. If this block is displacing down by a 10 centimeters length, is there any change in this part here? That length will be still 0.5 meters only will be there. And similarly, even if this block is moving down by 20 centimeters, the length of this part will be that 0.5 centimeters only will be there. Whatever its length is there, that length will remains constant. So that means with the displacement of these blocks, this length of the string on the pulleys or over the pulleys, they doesn't change. And so that no need of taking them, or even if you are considering them, you can consider like this. This x0 is the now length of the string over the pulleys. The effective length I am writing there. And so now we differentiate this. So now we will differentiate this equation here. dl by dt is equal to dx1 by dt plus here 2x is there. So 2x2 is there. 2 I am taking outside, plus dx3 by dt plus dx0 by t. And so now we know length of the string is a constant value here. So length of the string is constant. So its differentiation should be equal to 0. Is it clear? So this is our one of the basic procedure to solve the pulley problems here, pulley constraints. And next here this value dx1 by dt you can write it as v1, velocity of that block, and this value is 2v2, and this value is v3 and plus 0, right? Therefore our relation is v1 plus 2v2 plus v3 is equal to 0. And you need to remember that when you are solving the constraints, that means pulley constraints, by using this method, you will get the relation between velocity vectors or acceleration vectors. In vector form you will get here. And so now again differentiate this. To get, generally we need the acceleration relation here. To get the acceleration relation, just we need to use this differentiation of this. So dv1 by dt, differentiate it again, plus 2 into dv2 by dt plus dv3 by dt. This is equal to 0. Therefore this is a1 plus 2a2 plus a3. So this is velocity relation and this is the acceleration relation. Now this is nothing but our constraint relation here. So our constraint relation is this one. or we can write this as 2a2 is equal to minus of or a2 is equal to minus of a1 plus a3 by 2 you can write. Is it clear? So that is our vector relation. You need to note that this is our vector relation here. So remember that it's a constant only. Whenever you are writing, whenever you are following this procedure to write the constraint relation, you will get this vector relation only. Either velocity you may consider or acceleration you may consider. Why I am stressing this vector means in some problems you may get the confusion there. Or like suppose if you are following this procedure and if the solution is given somewhere in the other method, then that method may consist of scalar relation. So then they will give another answer. The plus and minus signs you will get confusions there. So if you are solving this, you need to remember that this is the vector relation you need to consider here, right? And so next you can solve the same constraint relation by using another method. That means just you may consider the displacement method. Displacement just generally after getting this and to complete this problem, you may consider the direction of accelerations here. You need to assume that. That means if you are getting this, if you are converting this into actual our magnitude relation, if you want to convert this is a vector relation. What I am saying, if you want to convert this into magnitude relation, you need to assume some directions of these accelerations here. Because why I am saying that you need to assume means you can't directly decide just by seeing the mass values here. You can't directly decide in most of the problems whether this block is moving upwards or downwards. Similarly, whether this block is moving upwards or downwards. In some simple cases, you may conclude whether the blocks are moving upwards or downwards. In majority of the cases, you can't conclude the direction of motion of the blocks. Then you can assume it any direction here. You can assume that block is either moving in upward direction or in downward direction. That is your choice. You can assume in any direction. So finally, and if you are assuming, for example, this in upward direction, this block is moving in upward direction, for example, then force equation also you should write by taking the same assumption here. That means if you are writing the constraint relation by assuming this block is moving upwards, and force equation if you are assuming that it is moving downwards, you will get the wrong answers. If you are assuming this block is moving in upward direction, in acceleration you need to take the constraint relation, you need to take the same assumption, and while writing the force equation also you need to take the same assumptions here. And for example, here I am taking this this block is moving in upward direction, I am assuming, for example, with acceleration a1, right? And so let us consider this block is also moving in upward direction with acceleration a3. Then this block will move down with an acceleration a2 here, right? In general, if this also if you are assuming in upward direction, then you will get the answer with the negative sign. That a2 sign you will get the negative, right? You suppose if these two blocks are generally by just by seeing the diagram, you can say that if these two blocks are moving in upward direction, this will move in downward direction. It may not be correct. This assumption may not be correct. This block may move down and this block may move up. Anything may happen there depending on those masses. If suppose if your assumption is wrong here, for example, then final answer after solving this problem, finally you will get this a2 value with the negative sign. That indicates that your assumption is wrong. Just you should reverse the direction of that acceleration. Numerical value will remain same. Just you need to reverse the sign value you need to reverse there. So what I am saying is you can assume the accelerations. If you are following this method, you will get vector relation here. This relation is vector relation, and you can substitute these accelerations in any method. That means you can take the directions of this acceleration as you wish. And suppose this is our vector relation. Now let us substitute these vector relations there. And now if I am taking this downwards as negative and upwards as positive, for example, then you can write this relation as these values will be minus of a2 magnitude. If you substitute, then you can write this the magnitude of a2 is equal to, now what we can write is a1 plus a3 by 2, right? Or that is nothing but if you are substituting the signs here, a1 is positive upward direction, a3 is positive, and this will be minus 2a2. If you substitute that sign, that indicates you are substituting magnitudes. And so that then you can write from this a2 value is magnitude of the a3 is nothing but a1 plus a2 by 2. And next if you want to write this force equations here, you can take the just FBD of these blocks and you can write this force equations there. FBD of M1, right? So FBD of M1 is tension is, suppose say here tension, taking the tension is also important. Let us see this. Here I am assuming the tension as T. Then here the tension will be T, and here also the tension will be T, and here the tension will be T, and here T. Because it is a single string only, so tension everywhere in this string will be same. T only will get, right? And so now the important thing is, if here tension is T and T, then tension in this string will be 2T you will get. This we discussed already in the beginning of this pulleys problems, right? So on the pulley it will be 2T downwards, and on this block 2T upwards. Or if you are representing only on the block, so let us leave that on the pulley. You may get confusion here. So that is only on the block I am representing here. So on the block this 2T will be there in upward direction. Why? Because pulleys are massless pulleys. The pulleys here what we are considering are massless pulleys. On the massless pulleys net force should be always 0. And so net force is always 0 means upward force is 2T is there, and so downward force should also be 2T should be there here, right? And so next, so then let us take this free body diagram. That is the tension distribution there. So this is T and M1G, and what we are assuming here is acceleration is in upward direction we are assuming here. So this is our upward direction A1 equation. This constraint relation now I am taking it as equation 1. And now let us write these values here. Then T minus M1G is equal to M1 A1. And next for FBD of M2. Now that FBD of M2 you can write this as, this M2 is there downward direction M2G, weight of this block. Here the tension is 2T. The important thing you should observe here is tension on this M2 block is 2T, and this block is moving down here. We are assuming this block is moving down with acceleration A2. And so now the force equation you can write this as M2G minus 2T is equal to M2 into A2. Next similarly FBD of M3 you are considering here. So the FBD of that M3 will be T upwards, M3G downwards, and then this acceleration of this block what we are assuming there is M3 is in upward direction, the acceleration of this block, and therefore you can write this force equation for this. So I can write that force equation as T minus M3G is equal to M3A3, right? And so now here, so let us name these equations here. This is equation 1 what we consider, this is equation 2, 3, and this is equation 4. Now you can observe that the need of that constraint equation here. So if you are writing only these force equations like this force equation for this M1 and force equation for this M2 and force equation for M3, if you are taking only force equations for example, now we can observe that how many unknowns are there, A1, A2, A3, 3 unknowns, and along with the tension 4th unknown. So by solving only these 3 equations you can't get this any value here, acceleration you can't find, or tension in the string also you can't find. So one more relation is required. So that relation is nothing but now our constraint relation. So which is the here, which is I mentioned here. So this is a constraint relation here, right? So then with the help of those 4 equations, now you can solve those 4 equations so that you can calculate the acceleration and you can find the tension in the string here. Tension in the strings you can calculate there, right? So that is the need of the constraint relations. So you can't solve only by writing the force equations. The accelerations between the different blocks in the system is required. So this is the for pulley, in case of pulley, this is the basic procedure to find this acceleration or constraint relations here, right? And so now let us see the another method. These force equations will be common for every method, whatever the method you are taking. That after finding this constraint relation, these equations we need to write like this only, and you need to solve that. So getting this equation only, different methods are there. So this another method what we can write here is so let us see that method. Just you may consider the displacement method here. Displacement method. just I am taking this as another method here, displacement method. But displacement method you can write only for few systems, but if more pulleys are there, then you may get some confusions there. So I am rubbing this part here because this part is not required here, x1, x2, x3, these calculations, right? So now let us say this diagram here. So in general, I will mention this general calculation there. From that you can mention this here. Suppose here let us consider this system here in this method, generally the displacement method, this one. So like this end of the string is moving down with an with a displacement say x1, and this end is moving with the displacement x2, and this pulley is coming down with an displacement xp. This pulley also, if it is moving down, if it is, then this displacement of the pulley we can write it as x1 plus x2 by 2. The average of displacements of these two blocks is nothing but our displacement of the pulley here. So that is in this case, right? If pulley is at rest, then xp value will be 0. That indicates x1 is equal to minus x2, which is our general simple awkward mission. So if you are writing this relation, then you can write velocity relation if you want, you can write, or acceleration relation if you want, you can write here. Therefore velocity of that pulley will be equal to v1 plus v2 by 2, you can write. This is velocity relation. And acceleration relation, acceleration of this pulley is equal to like a1 plus a2 by 2, you can write. So that is our acceleration relation. So that means you can write either velocity displacement relation if you know, you can write velocity or acceleration relation just by differentiating that. And you can apply it for a simple outward mission, then you will get the clarity about that. Simple outward mission, if you consider their pulley is fixed. If pulley is fixed, then what will happen is xp value will be 0. Xp value is 0 means x1 is equal to x2. This is also vector relations only. These x1, x2, v1, v2, these are also vector relations only here. The displacements what we are considering here. So that means you may put this bar here, the displacements what we are writing here, right? And next suppose if the another possibility is if suppose this x1 is in downward direction and this x2 is in upward direction, suppose this xp is in downward direction here. So then simply in this relation, this is a basic relation. In this relation now just we need to substitute with along with the sign here. So that we can write now, you can write this as xp is equal to x1 minus x2 by 2. Is it clear? Now this is magnitude only. We are substituting already sign here. So it is a magnitude relation only. This is a basic relation for any case. Now I am taking one particular case in that. So if this end is moving upwards and this end is moving downwards here, and a pulley is moving downwards. So this is opposite to that pulley displacement. These two are in same direction. So the direction I am taking as positive. So this direction will be negative, you will get. And so now similarly you can write this velocity relation, velocity of the pulley like v1 minus v2 by 2, and this is acceleration relation, you can write acceleration of the pulley is a1 minus a2 by 2, right? So if you know this basic, you can apply that case here. This is just application of that. This is a basic formula and this is application of that. So here it is not in vector form, you should note that. And so now similarly next suppose I am taking the case like one end is fixed for example here. So this end is fixed here, only this end is moving here. This end is say moving with x1 and this pulley is also moving with that xp. That means here this is not the fixed support here. What we are considering is if pulley is movable, we are taking that xp. If pulley is fixed, then xp value will be 0 in that if pulley is fixed. So that means don't confuse here how the pulley is moving down. If the total arrangement may move or it may fix. If it is fixed, then xp value will be 0. If the pulley is moving, then it gives the displacement of the pulley or velocity of the pulley, or we can say acceleration of the pulley. Now in this case, we need to apply the same formula here. Xp is equal to x1 plus 0. Here the displacement of this end is 0 here. It is a fixed end. So this end we are treating it as a fixed end here. So that this value xp value is equal to x1 by 2. And therefore velocity of the pulley is equal to v1 by 2. Or acceleration of the pulley is equal to a1 by 2 you will get. So that means the displacement of the pulley is given by this relation here, the basic relation. So from that you can calculate this, all these cases here. On a particular case you can apply this particular case here. So this will be useful in some velocity. There will be some problems just to identify the velocity problems there. So then this method will be useful for such a type of problems there. Is it clear? This is a general procedure to solve any pulley problems there. If you are solving by this method. And this method will be useful when there is some two or three pulleys are there, and generally when they are asking the velocity relations, they will ask some velocity relations. In such a cases, then this method will be more useful there. You can write that easily. So you need to remember the directions here. If we are assuming all are in downward direction, then we are getting this relation here. If one of them is in opposite direction, then we need to take that, or if it is fixed, then we need to take that value as 0, right? So that is that concept. Now let us apply this concept to our problem here. So let us apply this concept to our problem now. So there let us assume some displacements there here. So now I am assuming that this displacement of this block is x1 in upward direction. So if this displacement is x1 here, this x1 in downward direction you will get. So that means for our pulley. So in this problem now I am applying here. So let us see this. So this block, this side it is coming down x1 displacement, and this side let us take it as x3. Then this pulley is coming down, this pulley, or which is nothing but our x2 you may consider here, because the pulley displacement and this block displacement both are same only, right? So now all are in same direction only. Therefore the displacement of pulley or displacement of that block will be equal to, according to this formula, what we can write is x1 plus x3 by 2. So that is our relation. Now differentiate that twice, you will get acceleration relations here. So velocity of pulley, or this is velocity of the block 2, is equal to v1 plus v3 by 2, or acceleration of the pulley or acceleration of this block 2 is equal to a1 plus a3 by 2, right? So that is our velocity relations there. That means the velocity or acceleration. I think the final acceleration relation what we derived there. So that means the magnitude relation how it is. We substitute already signs here. This is the magnitude relation. So the magnitude relation is nothing but this one only, right? What we derived there. So that is another method for this writing the constraint relation here. And that is now after getting this, the remaining procedure will be same only. We need to write tension, that means force equation, free body diagrams and force equations. You need to solve that. And one more method is there here. So let us see that method now. And so which I prefer to solve the most of the problems here, which we call tension method. So now let us see this another method here, tension method. And this method will be more easy when compared to this remaining problems in any even complicated problems also. Even 3 or 4 pulleys or 5 pulleys may be there, then this method will be the simplest method for that. And so now in this method, what we need to consider here is, just we take the distribution of the tension here. And before going to that, the basic concept in this tension method is, here the tension is an internal force here. And all of you know the power formula in terms of this force. So that means now we know the power is, so we know the power P is equal to, we can write this as F bar dot V bar, right? We already in vectors also we already discussed that F bar dot V bar you can write, or which is nothing but you can express this as FV cos theta, right? And so now here the power delivered in pulley problems, what we can mention here is, in pulley problems, tension in the strings is an internal force, and so power delivered by tension to the system, to the total system is 0. Is it clear what I mentioned? The tension is an internal force. So internal force means it cannot provide any power to that system here. So that means net system, total system. For one individual blocks, if you consider, it may supply some power. For a whole system, it cannot supply any power here. Just if you are taking a simple Atwood machine here, if you are taking this simple Atwood machine like this, two block system, M1 and M2. I think all of you know the work done formula here, work done, Fs cos theta, right? And so now here if the tension acting on these blocks we know already like this. If we say M1 is moving upwards and M2 is moving downwards here. So now what is the work done by this tension on this M1 here? Is it positive or negative? If it is traveling a distance S for example, then work done on this block 1 will be T into S into cos 0. That means T into S, right? If we know if it travels a distance S in upward direction, then it travels a distance S in downward direction here in a simple machine. Now here this is T2 is W2 is equal to, for this now we can observe that T2 is in upward direction and displacement is in downward direction here. So you will get cos 180. So that this tension will be minus work done is minus Ts. So the net work done by the tension is we need to add the W1 plus W2, so which is 0. So net work done by the tension is 0 here. So that means the tension is an internal force. So it cannot, work done is 0 means power delivered will be 0. It cannot supply any power because power is nothing but rate of doing work, right? And so that what we can write here is the sigma, so sigma TV cos theta is equal to 0. So this is an important equation here. That means the total power supplied to the system we are writing here. The total power delivered to the system or supplied to the system, you can express it as sigma TV cos theta is equal to 0. So where theta is angle between this velocity and the tension here. Where theta is angle between velocity and the tension. Is it clear? Because the TV cos theta, that means here if you are writing FV cos theta, instead of F we are writing just a T. TV cos theta. Sigma we are writing means if more number of blocks are there, we need to add all those forces there. And so now for example for this system if I write here, so for this system let us consider here. So as I said, in this relation, in this tension method you will get a scalar relation. You need to remember that. You will get a scalar relation between accelerations. And so for that first you need to assume some directions here. To apply this method you need to assume some directions. So I am assuming this block is moving upwards and this block is moving upwards here and this block is moving downwards. So let it be A2. So as I said again, these directions are your choice. You can assume in any direction here. You can assume all in upward direction, all in downward directions also. Right? Finally you will get those values with the negative sign. Which are wrong, those values you will get the negative sign. So now let us apply this method here. So first for this I am applying here. Acceleration is in upward direction means velocity will also be upward direction. So for this tension is acting on this block will be along this direction here. So for this block tension and velocity both are in same direction here. So then T into V1 cos 0. For this block I am applying here. Next for this block if you apply tension 2T is in upward direction and velocity is in downward direction. We are assuming it is moving in downward direction here. Plus 2T into V2 into cos 180. Because they are in opposite direction, right? And next for this it is in upward direction and the tension is also in upward direction here, both are in same direction. So it is moving in upward direction. So T into V3 into cos 0. This is equal to 0. Right? So sigma TV cos theta is equal to 0. And so now write this. V1 T into V1 minus 2T into V2 plus V3 T into V3. This is equal to 0. You can cancel that T value so that you will get this relation as 2V2 is equal to V1 plus V3 you can write. And now let us differentiate this. Then you can write this as 2A2 is equal to A1 plus A3 you can write. So this is nothing but our constraint relation what we derived by using this either displacement method or by using length of the string method also, right? And so now observe this. You can write this constraint relation in a single step, right? With the help of this displacement method also you will get a single step only, but if there more pulleys are there, then you will get confusion in displacement method definitely, because here in this case you can identify the displacements easily there. If more pulleys are there, you will get confusion if you are following the displacement method. But this method will be easy for any number of pulleys. For any number of pulleys you can apply this method, you can solve it easily. Just only you need to identify this theta value angle between the V and the T here. And so for that you need to assume some directions here. So whatever the directions you are assuming throughout this problem, you need to consider the same directions only until you will get the final answer. So right. So that means sigma TV cos theta. So this method will be easy, and so generally we prefer to solve the problems by this method, sigma TV cos theta is equal to 0 method. So then now this is a scalar relation. Now you can write the force equations and you can solve that force equations there, right? So that means those are the three different methods to write the constraint equations for the pulley problems there. So just I introduced those three methods and I will explain some problems based on this in our next class, right? Thank you.